but no. Or something. I don't know what's going on with that keyboard, but does it really matter? So, anyway, in case you are curious, because this is just about the second most common question I ever get asked whenever I do these things, I am from Telford. Because I am always being asked that. And the third most common question I get asked whenever I do one of these things, it's there. Yeah, the first, incidentally, is, who are you? There we go. That's the least. I also wrote this book once upon a time. If anyone is interested in functional programming, which, I kind of am, it's kind of my thing, I wrote this book. It is a candidate for the silliest programming book ever written, because I wrote it, and that's the way I write them. I kept submitting silly ideas for stupid jokes to O'Reilly, and every time I expected them to just chuck their pencils at me, and every time they went for it and just said, yeah. This is the only book, for example, with a post-credit sequence. Absolutely true, it does. And a magic trick. I actually end on a magic trick. I'll leave you to buy a copy and find out what it is. Be prepared to be a little underwhelmed. It is a book. I'm going to be a co-host of a podcast coming up soon as well. This isn't out yet. This is coming out, I don't know, I'm told sometime soon. I am not the editor. I am a simple individual of simple skills. And most of them involve maths. But my co-host Leanne is working on this. So in our podcast, we are going to be taking, in each episode, a film which purports to be about tech and computers. And as three techies, we get around and see whether that is in fact the case. Spoiler, often not. We did The Terminator for our pilot episode, so look out for that. We have some very good ones, some very obscure ones, and some very bad ones. We did Weird Science. I did not like that one. That one made me feel icky. But I did really enjoy the first hacker film ever made in 1967, and you'll have to watch out for a bit more detail about that. So look out for it in the near future. I dare say I'll be screaming out about it on LinkedIn and so on. So here we go. I trained for this, so I believe that is said Haspazalmai, which I believe means hello in ancient Greek. I am learning ancient Greek, but I'm not that good. I can just about read the letters. First off, defining some terms. This talk is going to be about machine learning. Machine learning is a... Oops, that was a pile of rocks. One moment. I'll leave you in suspense. Machine learning is a subset of AI. That is, all machine learning is AI, not all AI is machine learning. Similarly, there is a subset of machine learning called deep learning. I will not be covering that, nor the broader aspects of AI. I am specifically going to cover this middle stripe here, machine learning, which, and I'm going to dispel some illusions here, is maths. I mean, anyone that tries to call it anything else is wrong. It's statistics. It's literally just statistical methods that have largely existed for hundreds of years, but applied by a computer that doesn't get bored and make mistakes in the same way that we do. So what is it trying to solve? Hence this. This is a pile of rocks. And this is the problem we're trying to solve in machine learning. So this is actually a thought exercise that someone in ancient Greeks came up with. And it runs something like this. So imagine that I'm building a big pile of rocks. So I get my first rock, and I put my rock on my pile of rocks, my one rock pile. And I will say to you, is this a big pile of rocks? No, it's not. Oh, no trouble. I'll get my second rock and pop it on there. It is now two rock pile. Is that a big pile of rocks? Probably still no. Okay, we'll carry on for some time, piling on rock after rock. And eventually, assuming my back does not give out, we will say, yes, you have finally constructed a big pile of rocks. Wonderful. I'll take one off. Is it not anymore? And no, of course, it's fuzzy. The boundary between big pile of rock and not big pile of rock is ever so fuzzy. How many rocks exactly does it take? What exactly is the cubic square inch size of big pile of rock? There are no answers to this question. The famous ones are, how long is a piece of string? A Jaffa cake, is it a cake or is it a biscuit? These are all questions with multiple, slightly fuzzy answers. I think it's a cake. And machine learning is an attempt to get computers to solve fuzzy problems with fuzzy answers. Because we can't just... Standard programming languages only work by saying a big pile of rocks is 7. Is it less than 7? No. Is it greater than 7? Yes. But with machine learning and statistical methods, we can move past that and actually give approximate answers, answers that work the human equivalent to sort of squint and take a few steps back and you can kind of see that it's right. That's the level that we're working at with machine learning, only hopefully slightly more clever than that. This, incidentally, is called the Soraites problem. Soraites, I believe, means grains of sand or something like that. It's the same concept. So let's first start off with some games, because I love games. You may see a few of these as we go through this. I am a parent, and as such, I love to play games with my two little children. And as a nerd, I want to ensure that I win. So before we start, this is going to be a little bit of how to analyse Super Top Trump's Harry Potter edition, which was the only edition I had to hand. My youngest daughter is going through a phase, bless. Does anyone not know how to play Super Top Trumps? You don't specifically know how to... Is that a hand? That's fine, that's fine, that's fine. You don't need to know how to play the Harry Potter edition specifically. They are all frankly the same game. Okay, Super Top Trumps, for those uninitiated. You take all the cards, they all got statistics on them. I think my next slide is... There we go. Here is Hermione. There's some statistics about her. Okay, sorry? Yeah, only marginally less fun. So how you play is, you take all the cards, there's a standard set of cards, I don't know how many, you divide them up between all the players, somebody starts and they say, I don't know, one of these, wand length, 10 3/4 inches. Everyone else says, what picks up their first card, what is your wand length? Whoever has the biggest wand wins, and they take all the cards. That person now chooses, and the play continues until one person has won all the cards. The game can last between 4 minutes and 4 years, depending on how the thing keeps bouncing back and forth. If I am playing, it does not last more than about 20 minutes before I just flip the table and walk off to do something productive with my life. Nevertheless, it's a good starting point for looking at statistics, because the point of Super Top Trump's Harry Potter edition is that we want to know which of these is a good one. We've got first year at Hogwarts, incidentally I believe earliest wins, wand length in inches, family tree, how many family members are there in the books, fear factor, and the rather arbitrarily denoted Top Trump's rating. Okay, and if we were playing with Hermione, we would have to select one of these to be our one. Well, which one? The only way you can know that is by comparing it to all of the others. So I did indeed sit down and go through every flaming card and write them all out so that I could start putting some stuff together. So a couple of very basic stats. When you say average to a statistician, they will say, because there's no such thing as average exactly, except it's three things with some extra bits. When most of us say average, we mean add them all up and divide by the number you got, yeah. But that is not what a statistician calls average, that is mean. There are three averaging methods. There is mean, median, and mode. Mean that's average. When you think of average, that's mean. Median is stick them all in an ordered line and pick the one in the middle. And mode is which one is the more of than any other. That's what those three mean. And really, you need to know both, although that's still not quite enough. But you can at least deduce some small pieces about these different categories by looking at these three, because there is a thing called data skewing. You've got the classic bell curve, but a skew means it either leans over this way or leans over that way. And in a classic bell curve, these three will tend to agree and have roughly the same value as each other. But what you tend to see here is they really don't. What this tends to suggest is that there are groupings on one side or the other which are pushing one of the methods from one side to the other. Classic example, mean and median roughly agree in somewhere in the early to mid 70s in terms of year started, but the mode is 1991. Which suggests that there are two clumps of data, which there are indeed. There are two generations in the books, and those two clumps of data are interfering with each other in terms of deducing. But you can see that in a glance by having all three, but that's still not quite enough to know how to go from this to how can we choose our best one in Harry Potter. All we can say is it's away from the mean or the median or the mode, but by how much? How much is significant? Going up 1 or 2 years in year, unlikely to be very significant, whereas top trump rating going up 1 or 2 might be very significant. And how can we quantify this? that is, oh, yes, a couple of bits of ancient Greek that I'm going to be using because I'm far too lazy to write out long words. Sigma means, that's sigma there. The ancient Greeks, if they ever pop forward into the future and looked at our maths, would say, why are all those letters all over it? Because that's just a s. That's all that is. That's an ancient Greek s noise. But it's called sigma, and that means add them all up. That one is mu, because it's not a Pokemon. It's because it's just pronounced m. And that means take the mean, add them all up, divide by the number you got. Okay. So to try and get some sort of idea of how much variance or how much our data set varies around, how much spread we've got, the first place we go is variance. Now I've tried to make this fairly language neutral because all of this can easily be done in just about any programming language in existence, but I just wanted to keep it neutral because although I'm a .NET developer, not everyone is. So take, for each one in the number set, take n minus the mean of the whole number set to give n1, and n2 is n1 squared, and then take n1, the sum of n2's divided by the length, and you've got the variance. That is the amount to which the data set varies around. And then take the square root of that, and we have what's called standard deviation. Standard deviation is your standard measure of how much things vary either way from the mean. In a nice classic bell curve, everything about, I think something, what is it? Something like 3/4 or so, or 90% of all the values should be +1 or minus standard deviation from the mean. And then everything beyond that is multiples of standard deviation, getting less and less significant in terms of representation of the mean as time goes on. So you can use this sort of a thing to determine how far from the mean are you in standard deviations, which gives you a standard way of classifying, am I far from the mean, am I right up close to it or not, irrespective of what your actual numeric range is. And then from there you can deduce, am I very far up, very far down, and you can work out whether this is a good value or not for the purposes of winning at Harry Potter. There we go. So you can see that for year, for example, a standard deviation is 23. Whereas for fear factor, it's 2.7. So you now got some sort of quantifiable value of where your new one on your current card falls with regards to the mean. So is it statistically high or statistically low? You can tell with this. When people talk statistics in the news, they usually miss this stuff out. Yes, averages are good, they're interesting, but without standard deviations as well, they're almost meaningless. Because you need to see how varied, how spread out is the data. That tells you, in some ways, far more than just the average by itself. Okay, and these are number graphs, so you can see there are indeed many skews. First year, massively skewed up over there towards the top because most of our characters are necessarily children, with a few outliers. This one down here, one person who started in the 1800s. Does anyone want to take a guess at which elderly wizard that might be? It's Dumbledore, indeed. Family tree, you tend to have either absolutely hardly any or flipping tons. I am, once again, for anyone who's seen or read Harry Potter, not going to take many guesses to see who that might be, with absolutely flipping tons of family. It's wrong. Fear factor, there you go, that's kind of clumping to the left over here. We've got loads that are not terribly scary, then blasting down slowly to people who are more and more scary as time goes on, and our top trumps rating seems to just be a flat number. It looks like they just went 1, 2, 3, 4, 5. So in terms of statistics, that is probably fairly meaningless. And that might even be deliberate to try and, but this is just correlations of the data to itself. That's not very interesting or useful necessarily. We can calculate how well do two columns of data correlate to each other. That is, by knowing one, can you necessarily say something about the other? So correlation is a measure to which two data columns correlate. That's the whole thing. I did all this, by the way, in Excel. Excel, it turns out, is a remarkably good machine learning tool. I'm as surprised as the rest of you, but it is. And especially when it comes to some of the maths I do later. It's really good at that stuff. But correlation is incredibly useful because when you're trying to design a machine learning set, an algorithm or a process, you need to know which of the columns to aim for. You generally know which column it is you're trying to calculate in your with your pipeline, but you need to know which of the various properties are the ones that are indicative of the value you want to end up with. And this will give you a value that is between -1 and 1. So 0 means absolutely meaningless. They might as well be random. 1 means they correlate perfectly. And by correlate, that doesn't mean they have the same value. They don't. What it means is they are in a perfect ratio with each other. As you double one, so you double the other. If you half one, so you half the other. Like that, in ratio, in proportion, not in value. Adding 5 to one does not add 5 to the other. That's not how it works. You'd have to find out what multiple that is, and then can translate that over. -1, on the other hand, means a perfect inverse correlation. As you double one, so you half the other. As you half one, so you double the other, and so on. But that tells us something. An inverse correlation is just as interesting and meaningful as a positive correlation. So I'm not going to talk through all of that, but you get the idea. It's just some maths. This is it written out algorithmically. Most of the sites that you come across will write it out as an equation, and I'm so sorry. Yes, they really are that hard to look at, but there you go. That's roughly the process. And that is what we call a heat map. So this is something Python does this, by the way. There's a little tool in Python that will do this really, really easily. If anyone's interested, I can point you at it. But this is each of the columns and the rows are the same data items, and then where the square where they match up is the correlation value. A strong red indicates a strong positive correlation. A strong blue indicates a strong negative correlation. Ignore the red diagonal line is the item correlating with itself. Pretty, but meaningless. But strong correlations, do we have any? We do. Wand length to top trump rating positively correlates 43%, which suggests that the makers of the game think that long wands is cool. I have no comment to make on that matter. -42% correlation between family tree and fear factor, suggesting that as someone has fewer family, so they become more scary. And that makes sense within the theme of the book series. Similarly, if someone has more family, they become less scary. Ron has many families. What else have we got? Wand length, yeah. Anything else? Oh, first year and wand length, -40% correlation, which suggests that as time went on, the trend became to have smaller ones. Could be, could well be. All of these things could be predictive, could be interesting, might be worth investigating if I was so inclined. I am not. This one is not particularly worth exploring with machine learning. It's interesting in terms of statistics. So let's turn to Pokemon. I am not a very big Pokemon fan, but during the pandemic I started playing Pokemon Go and I have not stopped. I have not played particularly any of the Pokemon games. I did try the card game once and it was kind of all right, I suppose. It wasn't very interesting, and I suspect it's a case of the richest player wins because they've got all this time and money to invest in an awful lot of very good cards. And I know what a completist I am, and I know I'd try and complete all the cards, and that's a fool's errand. That's not going to happen. I tried that with Magic the Gathering once until I basically had to stop myself because I knew where this was going. Nowhere good. Possibly having to buy a second house to store all of my Magic the Gathering cards. So we can come up with some predictive stuff to do with Pokemon. Let's have a look. This is a data set that I got off Kaggle. Is anybody familiar with Kaggle? Yeah, some nods. Yeah, some nods. Yeah, Kaggle, for anyone who's not initiated, is a fantastic resource site for machine learning. It's got a load of challenges on it that you can do. Some are deliberately designed to be simple for a learner. There's a Titanic one. I have another talk I did on that and solving that in .NET. And they had a data set of all of the Pokemons. Pretty sure the plural Pokemon is Pokemons. Well, I'm going to carry on saying it that way because it's funny. And we got things like attack, name is not very meaningful, height, attack over there, weight, is it a legendary, yes or no, lots of other stuff to do with Pokemon. So let's see what sort of predictive stuff we can do with this stuff. First off, our heat map. And this is a much bigger, much more involved heat map than all of the others. We got a whole load of very interesting dark squares. Just about everything correlates with capture rate, and they're all blue. This is capture rate here. It looks like as just about any statistic increases, your capture rate goes down, which makes sense. If you're bigger and meaner and more powerful, you're going to be harder to catch. I understand that. Base egg steps, that's how far do you have to walk before you start getting an egg off it. 87% correlation with being a legendary. The poor old legendaries don't drop many eggs because you don't want too many of them. Unlike Pokemon Go, where I have, like in the story, Mewtwo is something like this world-breaking, powerful character. I have 30 of them. I have enough to start a football tournament. It's Pokemon logic. Anyway, sorry, sidetracked. But one of the more interesting correlations, it's over there, is height with weight, 63% correlation, which makes sense, height and weight. With human beings, that's going to correlate really strongly. As you double someone's height, you generally speaking double their weight. Not necessarily, but generally speaking. Similarly, if you halve someone's height, I do not propose experimentally testing this, then you halve also their weight. And this is a scatter graph of height to weight. And as you can see, roughly speaking, I mean, this is Pokemon. And this is different Pokemons. Not, if I did this, say, with every single Pikachu I caught for an entire month, and I wrote down every single height and weight of every single Pikachu, I'm not going to do that. Really not. But this is, so there is a lot of scatter, because Pokemons vary wildly, because they're not real. I mean, like, sorry guys, they're not real. And some of them are literally made of steel. Some of them are actually made of air. And, you know, like, there is some real outliers way up around in the stratospheres of this. But generally speaking, there's a bit of a trend along there as height and weight, roughly speaking, correlate, because most of them behave according somewhat to sane physics and logic and biology. Somewhat. It is Pokemon. Like I said, one of them, yeah, it's Pokemon. So, what I want to make is an equation that will convert one to the other, according to the best fit graph. Given a height, what's the weight? Given a weight, what's the height? That sort of equation. And if I was, again, testing a million Pikachus and taking all of their heights and weights, so this would probably be super accurate, but for a bit of fun, I'm just doing it on every Pokemon. So how do you do it? Well, you've got X and Y, which are your two columns. So you donate two columns. These are whole columns of data, not individual data points, columns with loads of values, X number of values. You have a couple of intermediate ones you need, XY, which is X multiplied by Y, X squared and Y squared. You can probably guess what those are. And then you bump them into this thing. Yeah, it's a great big equation. If anyone's interested, I can bring any of these equations back. The slides are available out on the internet and there's books on this, but fine. What you're calculating is an intercept and a gradient. The intercept is the point at which it goes over the x-axis. The gradient is how steep is your curve. So and then the rest assumes it's simply a line. So the intercept is telling you how far left or right is it, and the gradient, how steep is your line. And from that point on, you have once you've done all of this crunching, the actual application is just a simple linear equation. All of this is how it tends to work with machine learning. You do ton of number crunching, but then what you get at the end is something that's incredibly simple and easy to use that a computer can do in moments. It's the processing and the creation of these numbers that's the hard bit. Once you've got them, very performant. So the calculation, this is what I calculated for a Pokemon. The weight is minus 12.47 plus 63.5 multiplied by the height. Height in meters, I think. So this suggests that for every meter of height a Pokemon gains, it gains 63 kilos of weight. And if you could have a theoretical zero height Pokemon, there's probably one of those, who am I kidding? Then it would have a weight of minus 12. And that's pretty simple. And that's what it looks like plotted against the thing. So yeah, it's basically a best fit graph line. That's pretty good. I mean, in a Pokemon world, that's going to be pretty scattered around, but it's still a pretty good best fit. That's not bad. To test how good it is, you can calculate something called error, and this is how you get it. Error is the measure of how well it fits. Okay, that is they call it error, and they call it residual sum of squares. They call it all sorts of things, but really what it is how, as a percentage, how well does it fit? So in this case, 39.7% fit. You know, that's my score of my. It's not great, if I'm honest, but you know, that at least I know. You just plug in these numbers and you know how well it fits or doesn't. and you know whether this is worth using or not. In the real world, honestly, probably not. But again, if I'd used every single Pikachu, it would probably be up in the 90s because it's probably going to correlate really well, especially as those Pokemon are procedurally generated anyway. So I'm basically slowly recapturing whatever the logic is that runs behind the scenes in terms of how this thing runs. So there is, to give you an idea though of how this can also sometimes be lead to interesting places, these are two columns from some data I got off the internet, which correlate really well. The first column is a year, and this is data point 1, and that's data point 2 over there. So I run these through my algorithms, and I get a correlation of 96.39%. That's a really good correlation. That basically means they correlate. That's very strong. Okay, there they are plotted against the graph. You can see they pretty much follow a nice little line there. Let's do a little bit more to try and work out our gradient intercept and so on, and we get y equals 603.1x minus 6553.8, and then plot that, and it looks pretty good. Actual against equation looks pretty good. I like it. That's fine. So r squared, that is what is the percentage fit, is 96.4%. Also really good. It's a great fit. It correlates really well. But what is it? It is the profits of Google against the sale of cheese. Year by year, they equate basically exactly. Does this tell us that by buying less cheese, we can cheat Google of their profits? It does not. The point is that correlation does not equal causation. It's not enough just to see a correlation. You also need to understand your data. You need to, all the correlation is telling you is that there might be some signal in the noise, but you need to still dig deeper. Does anyone listen to More or Less on Radio 4? Yay, I got a nod. Love that, one of my favorite programs. I recommend this thoroughly to anybody. If you want to understand the news, if you want to understand the statistics, or if you just generally want to be well informed, More or Less, basically people write into it on Radio 4 with a question about a statistic they've heard in the news, and they do a whole load of deep diving into, let's look at what do you mean by your terms? What's going on in this data? A correlation is not enough. Assuming correlation equals causation, that's got the formal definition, I think, is post hoc ergo propter hoc, after it, therefore, because of it. Something along those lines, but they do some wonderful analyses of what these numbers actually mean, what these terms actually mean. One of my favourites was one that's quite close to my heart as a West Midlander. There is a claim by two cities in the world as to who has the largest number of canals: Venice and Birmingham. I know which answer I will give. Birmingham. And what they did, incidentally, is they found out that it depends on how you define canal. If you define canal as something that some poor buggers went and dug out and filled with water, it's Birmingham. If, like the Italians, you define a canal as canale, which is any channel of water between two bodies of land, well, then it's Venice. But, loads of people can do that. That's how much digging was involved in Venice. I mean, really. So it's Birmingham, depending on how you define canal. You get the idea. You've always got to go a level or two deeper. Correlation is not enough. So, can you make this more accurate by looking at multiple points at the same time, multiple columns? You can, obviously. That's a rhetorical question. That's what we call these things. So for this, I will need some matrices. This, incidentally, has absolutely nothing to do with this film, although this is a very good film. We covered this one in the podcast. Has anyone seen this film? Yeah, it's pretty good, isn't it? How much has it got to do with matrices? Absolutely nothing. I just think they thought it sounded cool. It's a bit like the film Source Code. Has anyone seen the film Source Code? That's got nothing to do with source code. Production systems called source code. So, there's a source code, and they just thought it sounded cool, like this film. Anyway, this is a matrix. A matrix is a grid of numbers. An Excel spreadsheet is a matrix. But I didn't see Neo playing with one of them ever, did I? So this is going to involve an awful lot of matrix processes, which is just basically a shorthand for taking loads of little multiplications and adding them all together. And this is roughly how it works. So you've got two grids there in different shapes. And if you wanted to multiply these together, this is the process. You take basically you go through the row of the top one, the column of the second one, and then you take each pair of numbers as they match up, multiply them together, and then add all of those together. And then that gives you just the top left over here for the first row versus the first column of the second one. And then if you want to work out the second column, the top right of that one, then you go for first row of that one matched against second column of this one, and so on and so forth. It's all doable by humans, but it's so flaming tedious. Whereas Excel's got a whole ton of built-in stuff to do all of this for you, so it's a doddle. And there you go. You multiply these two matrices together, and that's what you get over there. It always has the number of rows of the first one versus the number of columns of the second. If I change the order of these two matrices, you would have not only different numbers, but a different shaped matrix as the answer, because that's how it works. The order is all important. These are the Excel things for doing this. mult for doing matrix multiplication. Transpose is take a matrix that looks like that and turn it into that. Now, inverse. Now, I did think, honestly, and I did originally have a whole load of slides about explaining inverse. Don't. Just don't. It's horrible. It's vile. Even trying to explain what a simple little 2x2 matrix inverse means would take me about 10 minutes. And then to explain any more dimensions than that, like, frankly, that's the rest of the talk done. Just don't. It's the equivalent of taking x and turning it into 1 over x. That's all you really need to know. Anything beyond that is just too heavy for a fun little talk like this. And why would you even need? Yeah. Anyway, so multiple matrix linear regression. So that is coming up with a linear equation, which is going to be simple and easy to use as the one I used before, but with 3 columns, because I had a look and I worked out which ones of these were the best correlations with weight, and they are height, the number of base egg steps, that is the number of steps before you get yourself an egg. I mean, I think that's how laying eggs works. You just walk long enough and an egg is there, and then it is born. I'm pretty sure that's how it works, or something. And then the defense, apparently that correlates too. So what you do is you have a matrix, which is all of your target training data. That is the data you've already got that you can use. It is a 1 across by x down. Then you get another matrix, which looks like this: a column of all ones, and then a column for each correlating data item. Okay, with me so far? Okay, transpose it. Fine, that is, flick it on its side. Multiply it by the original, get one of those. Inverse it, don't ask. Multiply that by this, the transposed one, to get this. And then multiply that by the original starting one, and then you get this. It's basically a weird shuffling trick. And this is a shorthand for a whole heap of just massive equations involving huge amounts of multiplication and addition. But thinking that shunting matrices around makes it all fairly simple to understand, well, you think you do, but you don't. But it's good enough for us to work with. So you end up with these. The intercept is the first one, and then the rest of this are your gradients. One gradient for each data column that you're starting from to get you to where you're going to. So that means that my intercept is now minus 70.5. The height gradient is 48.5-ish. Egg steps, it's 0.003. And hit points, it's 0.7. So those are my multiplication factors, and then add to that the intercept. And then you've got yourself a new equation. Weight is equal to 70.5 plus 48.5 times height plus 0.003 times egg steps plus 0.7 times hit points. And that gets you a new weight. And how does this... And this gives me a correlation of an error of 47.26%. It's ever so slightly better. There you go. It's actually quite a bit better. I've gone from a fit of 39.7% to 47.26%. So it's quite a lot better. It's a much better fit. It's fitting. I mean, you're never going to get perfect. This data is too wildly varied. But I mean, 47% fit. That's starting to sound a little usable, at least, if you really were bananas enough to try and do this. So let's talk about now logistic regression. This is similar. So that lot was all regression to go to map data types from one world to the other. We were mapping from height world into weight world. And we were trying to literally get any value out. We were trying to calculate what something's weight was as a continuous value between 0 and whatever the maximum weight of a Pokemon is. With logistic regression, we're trying to turn it into a probabilistic answer. What is the probability that a label is true or not? So in my case, I'm going with what is the probability that something is a legendary Pokemon, which is a relatively arbitrary label they've put mostly on large stompy things like Dialga here, rather than little cute things like Pikachu over there. I incidentally would pay money to see this fight. I know that it would last all of like 4 seconds, but I would watch that fight. Although it does always occur to me in these things, why is it always Pokemon versus Pokemon? Whenever Team Rocket pops up, it's always like, that Pokemon will fight. Or wouldn't it be just like, couldn't you just get the fire-breathing Pokemon here to just say, like, torch that man there until he is crispy, and now they will not pop up again? That seems to me to be a much fairer way, an easier way of dealing with these, but apparently no. Pokemon against Pokemon every time. Whatever. This is why they don't let me design these games. So we want to find all of the things that correlate as strongly as possible with is something a legendary or not, based on our heat map. So let's have a peek. Sometimes if you include too many data points, incidentally, there is a temptation to just literally stick everything in. You do that, sometimes you actually reduce, because some of these really don't correlate and are just going to add noise to your equation. So you really just want your top ones. And how much you want to include, how many, and to what extent, that is all more like art than science. And it's often a matter of trying a few things. But fine. So what correlates really strongly with being legendary? Base egg steps, we've mentioned this one before. There is a minus 41% correlation with happiness. Oh, legendaries are less happy. Oh, that's so sad. Capture rate is minus 33%. That makes sense. I mean, they're big and stumpy and hard to catch. Trust me, I've missed a few. Defense is higher a little bit. What else have we got? Attack is 41% correlation. That's pretty good. Generation, that is which generation of Pokemon are you, correlates 14%, which is meaningless because that's just a label and it means literally nothing. But at least you know it there. Hit points, higher hit points. Yeah, there's a few. The highest ones are base egg steps, happiness, and capture rate by the looks of it. They're the strongest indicators of something might be different about this Pokemon compared to your others. So those are probably pretty good ones to swipe and use in our equation. And popping it through the linear, this is first going through the linear regression algorithm, just to get, but what this is actually going to give you is, it should be a value between 0 and 1. So what you actually have here is basically meaningless. It's trying to calculate some arbitrary value between 0 and 1. It's not going to mean a lot. So you have to be able to convert this into a real meaningful probability. And it's like this. Take the exponent of the value you've just calculated divided by 1 minus the exponent of what you've just calculated. And then and the exponent, by the way, is x raised to the power of 2.718281 and so on. Why and so on, I don't know. It just is. I'm an engineer at the end of the day. I'm more interested in an engineer's answer to a lot of this stuff. I just want to know, how do I use it and what is it for? There it is. But math in C# there is math.exp or math.e or something which will do all of this for you. That's in .NET. I'm pretty sure that JavaScript has got similar, and probably so do most programming languages, or that a library that will bolt on and do it for you. So you don't need to worry about exactly what exponent really is. So this gives me a probability. There you go on the right-hand column over there. It's gone from being a predicted value, which in this as a binary state, the final answer 0 or 1. A predicted value means nothing. But in the column over there, it is now a probability that that is true. So can we compare that? There we go. And then I ran that again against every Pokemon in the whole set to say, is it a true positive, which is the green, a true negative being the green. True negative is, I thought it wasn't and it wasn't. Is it a red, which is a true positive, I thought it was and it was. With 2 tiny little stripes just about left. You can just about see them there, which are false positives and false negatives. That is, I thought it was or wasn't and got it wrong. So this, at least, is 98.88% accurate. Now, of course, my data set having clear signs of something existing makes this fairly easy. And you've still got about a 1.2-ish chance of being wrong, but that's still pretty good odds. We'll occasionally make a mistake, but we're mostly pretty right. And I don't know what those wrong ones are, but they're probably strange outliers that are randomly very easy to capture or lay lots of eggs or something like that, which is not in keeping with how a normal legendary works. So yeah, that's pretty good. That's pretty useful. Next up is the naive Bayes classifier. Now, I am, as anyone that knows me knows, a massive fan of Doctor Who. And so Doctor Who had to sneak in here somewhere. And I thought naive Bayes is as good a place as any, and also this episode's great fun. That's not AI, that really happened. The Space Museum, in case you're curious. Good one, that one. No, actually it's not, but that bit's good. Anyway, so these statistics are slightly out of date. So what I've done here is, for each Doctor in Doctor Who, I have put together a list of statistics. One is the number of stories that this Doctor appeared in. Now, have we got any real Doctor Who fans in the group today? Ah, good, because I don't like arguments. Yeah. How many stories have there been in Doctor Who? This is contentious. Is Trial of a Time Lord 1 or 5? I don't know. Depends who you ask. Is Flux in the recent series 1 or 6? I don't know. Depends who you ask. These are my numbers and I'm sticking by them. So, good. No one's going to argue that point. And of these stories, how many of them featured the Daleks? The Daleks, for anyone that's not aware, are the most popular baddies in Doctor Who. That's that. Oh, wrong. This, for the unenlightened, is the Doctor popping out of a Dalek. So, right. What I've got here is a list. It's basically a series of pots, right? All along. It's a series of pots. Each pot has a picture of the Doctor on the front that this pot belongs to. And imagine that there's almost like a series of balls in there, and each ball represents a story. The one colour to say it's a story with no Daleks in it, and it's another colour to say this is a story with Daleks in it. So you could rummage around in the pot and draw one out, and we can use some basic probability to say what's the chances that the Daleks are in this story. Some of the Doctors encountered the Daleks a lot. Hello, William Hartnell, who did it 5 times. Some of them barely saw them at all, or in fact no times at all, like poor old Ncuti Gatwa. I'm aware that these statistics are slightly out of date. He still didn't encounter the Daleks, poor thing. That's interesting. So this notation, by the way, with this, I don't think everyone can see that. It's not the best, but it's like a straight line there. Dalek line Doctor. That is the probability that Daleks are in it, given we know which Doctor it is. So given we know it's William Hartnell, we can work out the probability that Daleks are in it, because he had 29 stories, of which 5 featured the Daleks. That's simple, that's basic, that's school maths. But we can do something interesting with this. We can turn it on its head. We can regroup it using naive Bayes. Naive Bayes is this. The probability that A given B is equal to the probability of B given A multiplied by the probability of A over the probability of B. I hope you're all taking notes. There will be a quiz. It's regrouping. That's what we've done. I have a series of probabilities of probability of Daleks given Doctor. You can flick the A and the B around, and I can turn it from 13 pots or 15 pots of 15 Doctors into Dalek or not Dalek, and I can say the probability of a given Doctor coming out of that pot. Completely change the grouping from grouping by Doctor to grouping by Dalek. Now that's useful if that's really what you want to do with Daleks, but this is a simple, silly example that I'm doing for a bit of fun. There we go. So probability of Doctor given Dalek. So I have converted this into, like I said, 2 pots. Dalek stories, not Dalek stories. And now, if I run into my Dalek story one and draw one out, I know there's a 17% chance that it's William Hartnell. So I know that there is a 3% chance it's Sylvester McCoy, and so on, because I've completely regrouped everything using this equation, which is really ridiculously simple. It looks a bit scary, but it's not. This is actually used all the time in the real world. This is how spam filters work, for example. And what it's doing is taking a series of observations, probability that this occurs, probability that this property occurs. And all you do is take a whole load of emails that are not spam, a whole load of emails that are spam, and then you work out how many, given it is spam, how many of this property occur, how many of this property occur, how many, and so on. And then you can regroup to work out, given this property, what is the probability it's spam? And you can do that with as many observations as you like and combine them together to make yourself something that will come up with a fairly reasonable probability, given however many observations you want to include, that this is spam or not spam, or whatever. It doesn't have to be spam. It can be anything that has properties to which you can assign a probabilistic value. And you can do that however creativity takes you. So how it took me is, I thought, what could we use this to classify whether this is one or other of my favourite books, The Journey to the Centre of the Earth by Jules Verne, or The War of the Worlds by H.G. Wells. So I wanted to see, can I use a naive Bayes classifier to take a random sentence from one of them and then calculate which one it is based on the probability of each word and how likely it is to occur in that book? Answer, yes, you can. And incidentally, I didn't make it too easy. I am aware that Journey to the Centre of the Earth was written in French. I used an English translation. I'm not that lazy, although most of the translations suck. Anyway, so this is the process for making a naive Bayes classifier of this sort. Get all of the lines out of the book. Remove stop words. So these are little words. You can find lists of these online. It's dead easy. Little words that mean very little. A, the, of. Into sort of like gluing to get stuff together words, the stuff that's in every single book in the whole of the English language, pretty much. Remove punctuation, because that doesn't mean a lot. Remove one-word lines, because there's not enough data to actually make a decision on. Remove numerical words like the number O-N-E, 1, stuff like that. Take it, or literally a 1 character. Take all that out, because again, statistically doesn't tell us very much. And then what we end up with is a whole load of sentences like this. So the rather famous opening of War of the Worlds is whittled down to "one would believe last year's 19th century," which contains all of the more statistically significant words. No one would have believed in the last years of the 19th century, blah, 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 blah. That's that one. Okay. So that gives us something we can act on and we can generate statistics from. And this is the process. Take the word one, and briefly we have to assume that these two books contain every word in the entirety of the universe, because otherwise the maths doesn't work, but fine. Probability of the word given war is that. Probability of the word given journey is that. So basically, you can't create a probability of one or the other. You can create a probability of, is this War of the Worlds, given the word, and a probability of, is this Journey to the Centre of the Earth, given the word. But you start off with knowing that it is one, and that it's this word, and then you can work out how many times this word occurred, and then from that we can get some basic stats on that word. And it gives us a probability starting off that this is Journey to the Centre of the Earth, given the word, of 22%. And it's not Journey to the Centre of the Earth as it happens, it's War of the Worlds. And there you go. And what you do then is you basically aggregate. Take that, because initially we have to assume that the chances of this word occurring at all is 50-50, but now that we've put one word through it, we can run this again, and we can replace that 50-50 with a more up-to-date number, and then carry on doing that as you add each observation into the equation. And then bit by bit, it starts getting more and more accurate as you go down. Now, there, as I add each word in, this is what you kind of get. So we have an initial bit of weirdness at the beginning, but eventually, once you've got many observations, given that that is the first sentence of War of the Worlds, as of about 3 words in, it's pretty certain that it's now got a higher probability of being War of the Worlds compared to the probability that it's Journey to the Centre of the Earth, which is correct, and then it holds that for the rest of the process. So the more observations, of course, that you make, generally speaking, the more accurate your result's going to get. And so that's it. That you can use that on any random sentence from either of those books, feed it through this process, aggregate it through these equations, and then you get yourself a final probability. And then you just compare the two probabilities, whichever one's higher is the answer. And the accuracy of this was something ridiculous like 90-odd%. It's very, very accurate. Of course, this is based on two books, and there are certain high probability words that go in one and not the other. The War of the Worlds, for example, has a fairly high probability of the word Martian. Journey to the Center of the Earth contains relatively few uses of that word. More uses of the word dinosaur. Not many of those in War of the Worlds, although I'd pay to see that version. So you get the idea. And that's, again, how you classify spam. Right. K nearest neighbor. This is one of the nastier ones to actually use. All of the ones that we've seen so far, the pain is all at the beginning. And once you've done the pain, then actually after that, usage is easy. Afraid this one's the other way around. K nearest neighbor has its uses, though. This is probably less useful in production, during a production environment, because it's just going to be too processor intensive. This is trying to work out whether something belongs to a certain set or not, given what's nearby it. So it uses Euclidean distance, which is, you know, your basic like Pythagoras type stuff. Literally treat every data item like it's a dimension, and then try to work out in this 2, 3, 4, 5, 6, 100 dimensional space, which is the nearest existing data points to the new data point. And it's called K nearest neighbor because the way you get a more accurate result is you decide what K is, it's a number, and then that many nearest neighbors, if they're all inside data set A, then that's probably the answer. I've seen people demonstrate this, for example, by taking hundreds of GPS dots all over the UK and then using K nearest neighbor to work out sea or land based on, are more data points close to here in the land or on the sea? Most of the time it's easy because it's exclusively land or exclusively sea, but then around the borders, around the seashore, that's when it starts getting tricky, and that's when you start to have to say how many out of 5, how many out of 10, whatever. And then you can fill in any other data point that you want and decide whether it's land or sea. Good for that sort of a thing. So there you go, this is the process. Given a new data point, calculate the Euclidean distance between this new data point, and again, Euclidean basically for Pythagoras, and all other existing data points. You see, this is where it gets painful to use in production. Order by the distance ascending, and then pick the top K, whatever K is. K is whatever makes sense to you. I've gone with colour. Colour has 3 dimensions. Yeah, there's A as well, but it doesn't really work with this. R, G, and B, if that's the space that you're using, red, green, and blue. And you can quite easily, for any random colour, this is my random colour I generated, 221, 45, 65. And I got a great big data set online of colours with names. And I'm just literally going to work out the Euclidean distance between the red, the green, and the blue. And so that gives me a distance, a 3-dimensional space distance, imagining that there's a 3-dimensional space that consists of red on the X and green on the Y and blue on the Z. Once you go above 3 dimensions, this is where that sort of imagination just falls apart and you've just got to trust the maths. But I can work out which are the nearest data points around me to work out what's the name of this colour here. Makes sense? Pretty simple, really. You got a scary bit of maths here, which is all your, like work out the distance, square it, add all the squares together, take the square root of the whole lot. And that gives you your distances. Okay, so what is it? What is it? So, grey, for example, 84, 84, 84. If you run it through the numbers, it's got a Euclidean distance of 143.7. In and of itself, that number's meaningless. It doesn't really, what is the fact that it's this isn't really 3-dimensional space, it's just data points. But where it is useful is where you start comparing them to other distances from other colours. That's where it's useful. These are the 5 closest neighbours in Euclidean space. They are brown. It turns out that this colour is brown. Well, I'll be. Fair enough, okay. What do I know? But that's what it says. Might be, I don't know if the monitor's not great or what, but the Euclidean distance is, this is the nearest neighbour, called brown 3 and fire brick. And I suppose it's a sort of terracotta-y brown, I suppose. But there you go. Those 5 are all pretty close, and then you decide they're all vaguely shades of brown, therefore the answer's brown. That's it. Where this is or isn't useful, again, depends on what you're trying to accomplish. Now, decision trees. This is our last algorithm. Now, decision trees are far too complicated to really explain in a great deal of detail. They are horrible. And I could have done an entire talk purely on decision trees because they're that complicated. But generally speaking, as techs, as software engineers, we generally don't need to. There are tools that will generate these things for you. So what I'm going to do instead is try and demonstrate what the usage is and what it is you're trying to accomplish by creating a decision tree using the medium of Guess Who. Does anybody not know how to play Guess Who? Anybody? Yeah, that's fine. Don't worry about it. It's fine. Okay, this was one of my favorite games growing up. This specific edition, I scoured the internet for this exact edition because this is the one that I used to play as a little kid. How it works is you get a card which has one of these faces upon it, and that is your person. This is hidden from the other player who has one of these grids. You each have one of these grids and each have a card. Neither of you know the other person's person, who they are, and you can ask yes or no questions, and based on that you can flick, because these are all like on little hinges, you can flick these people down to say, well, I said, does your person have hair? And you said yes, therefore... You're right over there? Yeah. So if I say, does your person have hair? And you say yes, then all the people who are bald can all get flicked down because I know it's none of them. And so on, and you keep asking each other questions back and forth, back and forth, back and forth, until somebody deduces, because there's only one left, who is your person. It is a very stimulating game. Actually, if you want to be really advanced, have 2 people at the same time, and you can only say questions like, do either of your people, blah, blah, blah. Now that's the way to play it with the grown-ups. That's tough, that one. Anyway, how do you play this to win? Because that's what we want to do with a decision tree. So you can go for a high, something that has a small number of yeses and ask that. There is a small chance that you'll get a yes, in which case the game is yours. But there's a much bigger chance that you'll say no, in which case we'll just flick down a couple. So what you really want to do in order to win is to ask a question that eliminates half of the people that are there all at once. Because it doesn't matter what they say, it'll eliminate half of them. And then you've got to fit. You'll basically win the game in maybe 4 turns. I think roughly is how that works out. Okay, so let's have a look. What questions can we ask? Hair color. Well, no. The most common hair colors are black, red, and blonde. And there's a maximum of 5. There are, by the way, 1, 2, 3 times 1, 2, 3, 4, 5, 6, 7, 8. 3 times 8, somebody help me out. Sorry? 24, thank you. I'm great at maths, terrible at mental arithmetic. Apparently that's a thing. At least that's the way I'm going to tell people. 24, okay, so that's not very good. So you can't use that. Gender. In the real world, the probability of a random selection of someone and their gender is 51% female, 49% male. Clearly not in Guess Who. Now, this is not a sexist thing, necessarily. Maybe the picking of male rather than female as the 19, possibly. But I think they deliberately chose not to make it 50-50 because otherwise it's too easy. Everyone's going to ask that as their first question. So, there you go. 5 women to 19 males. No, once again, not useful. I looked at all sorts of things, and I really did look for all sorts, and no, nothing has anything better than 7. That's the closest I can get to 50-50. 7 versus 17, that's no good at all. That's if you've got facial hair or not. I mean, of course, this is a deliberate design choice by the manufacturers of the game. They don't want you to be able to pick something so easily. There is a way, in case you wanted to know how to win at Guess Who, I am about to spill the beans. Compound questions. Yeah, this is also a great way to make yourself lots of enemies. So, does your person have a hat or glasses or jewellery or earrings or a bow? If the answer is yes, 11. If it's no, 13. So I don't care which answer you give me. Pretty good for me. Is your person female or has facial hair? Or has 13 or 11. That's pretty good. Hat or glasses or blue eyes? Yes, 13. No, 11. None of these are 50-50. If anyone actually manages to get an exact 50-50, let me know. I'd be interested. But these are the best I could get. And yeah, this is ridiculous. But the point is that I want to make a question that will split the group 50-50 so that I can make my first line of assessment. So I'm going to play an imaginary game of Guess Who now, imagining that this is something that's been constructed with a decision tree. So first off, female or facial hair in my imaginary game of Guess Who. What's the answer? Yes. Yes, one of those things is true. Okay, so I can eliminate a whole load of people. Pretty good start. But here's the kicker. For my next, I can't just go back to those questions I started at the beginning. That doesn't work. It's got to be a new question based on who is left on the board now. I want to eliminate half of the people who are left now, given that I've already eliminated roughly half. Make sense? So question 2, beard or blue eyes, 6 or 7. Of the remaining people, that's about half. So I don't care what the answer is. I'm going to eliminate a load of people. No, neither of those things is true. A whole load more eliminations. Not many people left. 2 questions, and I'm really close to winning. And 1, 2, 3, 4, 5, 6, 7 people left on the board. So odds are looking pretty good for me 2 questions in. Black hair, my next question, because there are either 3 that do or 4 that don't. So once again, roughly half. There's 7 people left, so there is no 50-50 question. It's always going to be 4-3. So this is as good as any. No, not black hair. Ba-ba-bang. Not 3 questions in, and we have 1, 2, 3, 4 people left. So there's got to be a few things that I can eliminate now easily with 50-50. Now, notice that we have 3 women to 1 man. I never asked the question. The classic question, almost everyone I've ever played Guess Who with is, are you female? Is your person female? And I've not asked that, but it's kind of sorting us that way anyway, because that's the way the data's leaning now. Okay, so hat. Yeah, if you look, 2 people are wearing a hat, 2 people are not. And again, based each time on the data that remains. Bang. Yes, they are wearing, one of them it's someone wearing a hat. There are only 2 people left, so I may as well just ask a name. Is it Maria, my personal favourite in this game? Yes, it is. I love Maria. She's the best. She's so cool. So you get the idea. If you were a machine, and now a real decision tree is much more complicated than this. It's not trying to win at Guess Who. It's trying to sort things statistically. And it's not going to be, it might be binary things. That's one way that you can work with a decision tree. You can make a probabilistic barrier between category 1 and category 2. Or it could be a range of values. Is this value greater than this or lower than this? Or some sort of compound answer like before. But the maths behind this is so phenomenally complicated that it's really far beyond the scope of this. And I would argue that 95 to 99 or more % people who ever work in machine learning don't really need to go through the process of understanding on pen and paper how to construct a decision tree. But this is what it's doing. And the beautiful thing about it is that once again, like most machine learning algorithms, you spend ages crunching the numbers from the training set, because I didn't show you, this is just operating a machine learning, a decision tree. The questions would all be calculated by the training process, and then it would come up with the whole tree, which is, given this answer, here is the next question to ask. Given that answer, here's the next question to ask. The entire tree, every possibility from yes or no at each level, and we've got all of the answers going down, but actually operating it is just a few questions. So in production, these things are really, really fast. They take time to generate, to create, but really quick to run. So they're very, very performant. And these tend to be the machine learning algorithms that give you, in general, depending on what you're trying to accomplish, your best results. The Titanic challenge, for example, if anyone consider the Titanic challenge on Kaggle, it is given a set of statistics about each passenger on the Titanic, calculate whether they survived that night or not. That's the Titanic challenge. And decision trees is how you do it. Spoilers. But that is how you do it. Part of the rest of the trick is deciding which fields you're interested in and then maybe doing some extra calculation. There's a lot. That particular challenge is as deep as you want it to be. But decision trees is how you get your answer. Okay. That's it for algorithms. So if anyone is interested in any further reading on this subject, because I certainly have enjoyed reading up on this book is a basic statistics book. It is an excellent book on statistics. I have had it on my bedside table for quite a long time because I am that sort of nerd. And if you really want to understand machine learning, you've got to start with statistics because that's what it is. It is statistics. I have also been recommended this book. This book is available on the internet at this website for free. And free is the best price. But one of my friends has a PhD and recommends this book, so possibly this book is the one to go for. This book is also excellent, the 100-page machine learning book. It is basically like a thumbnail sketch through the whole of the machine learning world. It's a good starting point. It's a good place to know the basics and know the questions to ask to go further. This is also available for free at this website. I have a paper copy at home because I like to read it in bed. Yeah, okay, I do. What are you going to do? And, all right, here we go. Aegarti punthanaiton aite ermeneuton. That does not mean whose phone is that. That means, does anybody have any questions?